Welcome back. So, in previous lecture we discussed about mainly the body wave, P wave and S wave, and we also discussed about that why they are unable to, one of the wave, that is your S wave, is unable to travel through the interior of Earth because of its property. So, this is a similar diagram which explains the propagation of the P wave and the S wave. So, on the left hand side, if you see, if we trigger the earthquake here at this point, then you will have that the P waves will not be recorded in this region because they are getting diffracted. So, P wave cannot reach the surface within the saddle zones. This one is the saddle zone for the P wave because of the way they are refracted when they enter and leave the core area, because the inner core is solid, whereas the outer core is liquid. So, from here they will be refracted, and because of the change in the pathway of the propagation, they will not be able to reach this region. So, this portion will mark as an P wave shadow zone, whereas the S wave reaches the core, they cannot travel through its liquid outer region, that is the outer core is liquid, hence they will not be able to travel through there, and therefore never emerge beyond 105 degree from the focus, that is the point at where they are generated. Hence this whole area will be your S wave shadow zone. So, please note down this one, that you have if you are having triggering the earthquake at 0 degree, then this region, that is almost the variation of 40 degrees, you will not be able to receive any P wave, and this zone has been termed as P wave shadow zone. So, P wave shadow zone is from 103 to 143 if you have triggered the earthquake at 0 degree, and the S wave is from 103 to 180. So, from this point to this point here, you will not be able to receive. So, if you are dividing the whole earth into half, then you will not be able to receive the S wave. So, S wave shadow zone is from 103 to 180 degrees. So, this is further to understand the propagation of the P and the S wave. So, S wave has been highlighted with the pink color, and the P wave is with the blue color, and this all locations which are been shown here are the stations. So, suppose you are triggering the earthquake here, that is, if you take this on 0, 90, 180 and 270, then in this region you will not be able to receive any S waves, whereas the refracted P waves will be received in this region. So, P wave and S wave paths from an earthquake, if you take, then what has been shown here is that you have some reflected waves which are coming from the contact between the mantle and the outer core you have, and then some which passes through, and with that these are the refracted waves of P, and then we have also the reflected S waves which are been received by the stations which are sitting here. So, different terminology has been used. So, P and S waves radiates from an earthquake focus in all directions. Now, so the diagram simply labeling the scheme the seismologist uses to describe the various path of the waves they take. So, PCP is here, this one is the PCP, and SCS SCS is over here. So, these are all like our compressional P waves, we have this one, and the shear S waves that bounces off the core. So, they are just reflected back and they are received by the stations. PP are over here, this one waves are internally reflected from the earth crust. Then further we have PKP. PKP is over here, is transmitted through the liquid core, and a PKI KP is this one, which is further are been reflected from the inner core. So, when it enters here and then when it goes out of that. So, surface waves propagate along earth outer surface like waves on the surface of ponds. So, this is another category of waves, that is the surface waves, as compared to what we have learned about the body waves. So, P and S waves and the surface wave paths from focus to seismograph. So, seismogram is the instrument which records the P and S waves, and or we can say that body wave and surface waves. So, the instrument which records the seismic waves is termed as seismograph, and the data which we will get is termed as seismogram. So, these are all what has been shown here as the seismogram recorded at various distances. Okay. So, this is seismograph is the instrument, and the recorded one is this one is your seismograms. So, depending on the velocity it reaches at different time. This has been shown as the time in the y axis, and you have the distance where different seismographs are located, which shows the arrival of the P wave and the S wave. And here what has been shown here, you are having the P wave, then the S wave. So, P wave will arrive first, then the S wave, and then SS, which is again shown here, which are reflected from the surface of the earth, and you are having the surface waves. So, S wave, when they travel, they will just moves the material up and down, whereas the P wave, which we have seen, they usually push and pull the ground. So, this wave is comparatively dangerous because it will move the surface up and down and will result into the partial damage. So, similar to this what has been shown. So, particle moves up and down and the surface moves up and down. So, this moves the motion is up and down in the direction of the propagation. So, during several earthquakes, some features are been left out on the earth's surface, and this is one of the example from 1999 Chichi earthquake of Taiwan, where the S wave has moved and resulted into the down and up of the region, and also the damage which is resulted by that. Similarly, we observed during 2001 Bhuj earthquake. So, the waved up bridge here is because of the passage of the S wave. So, any building or any structure sitting on the top of the surface will experience this up and down, and similar was the case as in the epicentral area in 2001. You can see the waved up surface because of the passage of the S wave. Now, such signatures of the passage of the S wave and all that can also been taken into consideration. So, suppose you are having as we have seen in the Chichi earthquake, that you are having the structure which was like this, okay, very well constructed, and because of the passage of the S wave, then you will find that the structure has been waved up. Now, this features can also be taken into consideration when we are looking at the archaeological sites. Okay. And to some extent, we were able to see the wave of platforms in the archaeological sites wherever they were being exposed. Okay. And this understanding helped us in knowing that that particular site was affected by the passage of the seismic wave. Then coming to the next one, that is the surface wave. We have love wave. Now, the love wave is having the combination of both. It will make the surface move up and down as well as side by side. So, this is a typical way of the propagation of the S wave. The particles are moving side by side and up and down, whereas the relay wave, you have an elliptical motion, and the direction of propagation is in the same, the direction of the wave motion is in the same of the direction of the propagation of the wave. So, the love wave will move the surface side by side, whereas the elliptical one will move the material up and down way, where for example, if you are having two buildings sitting close to one another, or you are having the light poles or trees, they will bang at certain point because the oscillation of these two structures will be different. So, this will result into the collision and more destruction. So, the surface wave, when it moves, then it will completely destroy the structure. So, in terms of the S wave, what we saw is this was partially damaged, but during the propagation of the surface wave, this will result into total damage. So, in short, if we take into consideration the wave types, body wave and S wave, motion, longitudinal transverse for the body wave, that is P wave and S wave, and horizontal transfer love wave, and then you are having vertical elliptical relay wave. So, this you should remember, because this is going to be helpful while understanding the overall damage pattern also. Now, coming to the earthquakes, some of you must have experienced the earthquakes, because we have experienced in 21st century mostly like 2001, then we had 2004, then we had 2005, then we had 2015. These are I am talking about the major destructive earthquakes. So, 2001 was in Bhuj in the western part of India, and 2004 was in Andaman Nicobar subduction zone region, and 2005 and 2015 in the Himalayan region. So, as I was been emphasizing right from the beginning, that we have three major regions, seismically active regions, and all these three have experienced earthquake in a span of hardly 10 to 15 years, okay, starting from 2000 to 2015. So, earthquake process is important before we get into the details of value seismology. So, earthquakes usually are the sudden release of the stored energy within the earth crust, and will result into the displacement, and the manifestation which we see on the surface will be something like this, okay. and these are the features which we are going to learn in detail. To that such features we will pick up and will try to understand that what is the history of earthquake on such features which are termed as fault lines. And since they are active and capable of triggering earthquake in near future, hence we term this as an active faults. So, this photograph which I am showing, the aerial photograph of the San Andreas fault system, very sharp feature that exists on the earth surface, indicative of past tectonic deformation and are likely to trigger the earthquakes in future along this line. So, this is an example of a right lateral shift. So, whatever the landforms you see on the surface will also get modified because of the movement on the earth that reaches the earth surface. So, one side what we see is then here there is a very sharp line, and the landforms, that is your surface, okay, is been modified where this portion is up and this portion is down, and the movement which has been shown is by these two arrows, that this block of the crust has moved in this direction and this is moving away from us. Okay. So, this is towards right, hence we term this as a right lateral strike slip fault. This is the strike, that is the orientation of the fault, and the streams which are flowing from here are been deflected along this line, and this will keep like the records are preserved on the earth's surface if they are not eroded, and then one can quantify that what is the amount of displacement which has occurred along this particular fault. So, for example, this stream has been deflected covering a larger area as compared to this one, hence we can say that this was this stream recorded or was deflected during the recent or young earthquake, or but this one is having the cumulative amount of displacement. So, if you take this length here, okay, so this will be almost like twice over here. Okay. So, this stream has moved in more than one event or one earthquake, and this one during one single earthquake. So, this you can easily make out using the expertise or the understanding of the landforms which are preserved on the surface. So, this is going to play an important role, and then this what you can mark is the fault line, and this is what will play an important role in doing the initial identification of active fault. Now, earthquakes basically we see, and the movement along the various fault lines is important, and this is one of the best example which has been given by USGS, that if you take your both hands and try to press along this contact, and you apply force from your both the arms and try to move along this one. Okay. Either you move towards your hand, right hand side towards your side, or you move this away and try to move with the pressure here. So, you are applying force, and the strain is building up or stored here along this line, and the time will come it will slip. So, when it slips, it will give a sort of an jerk on your either on your hands, and that jerk basically is your earthquake. Similar thing happens in the interior of earth, but what is important here is that how many such weak zones, because this here we have just marked one weak zone here, but if you are having multiple weak zones and if you are compressing those weak zones by applying force. So this, for example, if you are taking these two arms, but if you say that these two arms represent the plate, different plate, one plate here, another plate, and they are colliding or trying to slide along this weak zone, then they will, and what rate it will slip. So in US, and the most active zone is the San Andreas fault system. So San Andreas fault system is not a single fault line along which the slip occurs again and again, but it has many slip planes, and all the slip planes or the fault lines, they behave differently in terms of the slip. Okay. So for example, on this fault, okay, we are having this slip is around 3 to 4 millimeter, whereas on this fault it is around 17 millimeter, and the 9 millimeter and the 6 millimeter, and here along this one is almost along the 15 millimeter. So all these faults are slipping at different rate, and this data is important for us because the larger the amount of slip consumed by the respective fault, the chances of having the earthquake will increase in terms of the recurrence. Okay. So the time period will be differ on of the occurrence of earthquake on this different fault. For example, this portion is having almost 24 millimeter. So the recurrence along this fault line will be shorter as compared to what we see on the other fault lines. So another example which was been shown is that if you take the instead of just your two arms or the palms, you put the playing cards, which are these playing cards are having different contacts, and try to move. So they will not move at the same speed or the same velocity. They will slip at different rate, and that is what has been given here. So for example, if you consider that this slip is taking place between the Pacific plate and the North American plate, which is the North American plate is moving like this, and the Pacific plate is moving like that. Okay. So the different fault lines which are formed, or the weak zones which are formed because of this deformation, will slip at different rate, and that what has been shown over here. So you are having different slip rates per year. It has been given in millimeter. So this can be identified based on the paleoseismic investigation, as well as this can be done using high resolution GPS measurements. So North American plate and the Pacific plate. Now deformation of rocks under tectonic stresses. So any rock or any location you take, usually it gets into the deformation pattern which has been shown here in a simple way. So you have you keep applying stress, you keep building up strain here. So the Earth's material in the Earth's crust will initially deform elastically, and after the elastic limit of any material, it will get into the deformation of ductile deformation. So this is an elastic one. That means if you apply the stress up to this point, then it may come back, okay, because this is deforming elastically. But after some time, then it will enter into the ductile. So what we see, the folding of the material, and finally if you keep increasing the stress, then the point will come, it will fracture this. So this is the threshold limit of any given material, and this fracture will result into the displacement, and this point at which it will fracture is your earthquake event. So elastic deformation is reversible, whereas the plastic one, that is your ductile, getting into non-reversible, and then brittle, that is your failure, and that failure is on the fault slip, and that failure or the fracture is your earthquake. So, with increasing stress, a rock deforms elastically and then plastically before ultimate failing or breaking, that is your failure, okay, which is an earthquake. A complete brittle rock fails at its elastic limit. So, different rock or the material in the earth will have different elastic limit and plastic limit. So, depending on that, you will have an failure. So, this is one very basic fundamental diagram which explains the deformation pattern of any material, that is in the elastic, plastic and brittle form. Now, this deformation pattern will be different at different depth of the interior of earth. So, for example, if you take the cylindrical core of marble or any material, then initially if you have so if you keep applying the same amount of stress, it will deform differently at different depth. So, this is what has been shown here. Okay. So, you have under the condition represented and shallow crust, okay, where the marble is deformed in a brittle form. Okay. So, you will see the fracturing. Okay. But at the greater depth, what you are having, the deeper part of the crust, where you have high temperature and pressure. So, it will deform in a ductile manner. Okay. So, it will not break, but it will change the volume and it will deform in a ductile fashion. So, we can easily talk about that if the deformation is restricted to the shallow portion, then we are going to see more faulting and earthquakes, whereas the deeper one will not result into such deformation. So, this will be more dangerous as compared to the earthquakes taking place in the deeper part. So, this is another example which has been given, that we have the stress pattern. If we take sigma 1, sigma 2, sigma 3. So, in the deeper part we will have uniform stress, whereas in the surface close to the surface of the crust, then we have differential stress. Okay. So, mostly what we see, the deformation pattern, that is the building up of the mountains and the fracturing on the surface, is because of the differential stress. So, where you have the sigma 1 is the maximum and intermediate and minimum one, sigma 1, sigma 2, sigma 3. So, for example, further if you take the uniform deformation, this is the picture of granite, then you see that they are uniformly deformed, but if you subject the same rock to differential stress, then what you see is then preferred orientation. So, the granite consisting of quartz, feldspar and mica, which have been shown here, the darker ones, will crystallize under a uniform stress, and mica grains will be randomly oriented. So, this is what randomly orientation has been seen during the time of or under uniform stress. But when they are subjected under the differential stress, major as well as minor grains, that is we are talking about the minerals here, will orientate parallel to the parallel along with respect to one another and perpendicular to the maximum stress. So, they will be aligned or oriented perpendicular to the maximum stress direction, giving rise to distinct foliations. So, in metamorphic rocks we see foliations which are indicative of that they have undergone in the deformation of the differential stress. And similar thing happens on the earth surface, where you see the formation of the folded mountain chain, which are parallel to one another, but they are exactly perpendicular to the higher stress direction. Okay. So, this is just to show the fracturing pattern. So, you will have mainly the conjugate faults which are developed if you have the brittle deformation. Then earthquake forecast and prediction. This is another important one, where the seismologists mainly use this information to predict or forecast the earthquake, and this is basically based on the micro seismic activity, the recording of the micro seismic activity. But this sometime it has proved successfully. They have been able to identify the event successfully, but in most of the cases they failed. But yes, of course, if you monitor very precisely, then one can easily make out that there will be a major earthquake in near future. So, forecasting identifies both earthquake prone areas and man-made structures that are especially vulnerable to damage from shaking. So, the ultimate goal is to reduce the damage pattern. So, the forecasting is important for the earthquake prone areas as well as for the man-made structure, whether they are vulnerable to the particular earthquake or not, and in particular region. Okay. So, earthquake prediction refer to attempt to estimate precisely, okay, and that is why I have put the question mark here, that to some extent we can, but not always, okay, when the next earthquake on a particular fault is likely to occur. So, I will stop here, and I will continue in the next lecture. Thank you so much.